Okay, so last time we have seen that the proportion of molecule we have sufficient large activation energy, and for bromination and chlorination the needed energy of activation, uh, it plays very important part in the selectivity of the this halogenation radical halogenation reaction. So we have seen in previous part that chlorination reaction is favored by 30 kilocalorie per mole for secondary halogenation, and for primary halogenation it is favored by 27 kilocalorie per mole. So here if we will observe the energy difference in when bonds are breaking, at that time the energy needed to break the bonds, it's 156 kilocalorie per mole for secondary halide formation, and 159 kilocalorie per mole for primary halide formation. And the same thing we have observed in case of bromination reaction. For secondary bromide formation, the energy needed to break the bond is 145 kilocalorie per mole, and for primary halide formation, it needs 147 kilocalorie per mole. So here favored by it's 8 kilocalorie per mole. So energy difference in between these is 3 kilocalorie, 145 kilocalorie to one. It's a 3 kilocalorie per mole for bromination, and for chlorination this difference is also 3 kilocalorie per mole. Now next point, if we will see, for selectivity for bromination versus chlorination is proportional to the difference in activation energy for the K step. Okay, so the K step here is nothing but the breaking of the CH bond. Okay, so the CH bond breaking, and for the so keeping reaction temperature constant, we have to measure for activation energy for each reaction. Okay, so we are going to measure energy of activation by keeping temperature constant, and two different halogens and two different CH bonds. So we are going to see the activation energy for each reaction has been experimentally measured. Okay, so that we have reference how they have experimentally measured the activation energy to break the activation energy of CH bond breaking. Okay, so that is propagation step, and this is the K step of the reaction, and everything is depend on this reaction. And if we will check out the activation energy of this reaction of this K step, then it will it makes the idea clear cut, how why the bromation reaction is more selective than the chlorination reaction. So here, as this thing, I promised energy of activation for first propagation step of radical halogenation, that is like this. For secondary halide formation, the energy of activation is 3 kilocalorie per mole, and for primary halide formation, in case of chlorination, energy of activation is 4 kilocalorie per mole. So you can, if you will see the difference in between these two, primary halide formation and secondary halide formation is difference in energy of activation is only 1 kilocalorie per mole. The next reaction, bromination reaction, primary bromide formation, secondary bromide formation. So energy of activation in generation of this radical or breaking of CH bond. So for secondary bromide, in case of secondary bromide formation, it's 13 kilocalorie per mole, and for primary bromide formation, primary alkyl halide formation, alkyl bromide formation, it's a 16 kilocalorie per mole. So energy of activation, difference in energy of activation in between secondary alkyl halide and primary alkyl halide is 3 kilocalorie per mole. Okay, so if you will see carefully, the difference in between the chlorides is 1 kilocalorie per mole in case of chlorination, and in case of bromation the difference is 3 kilocalorie per mole. In K step of reaction, K step is nothing but the CH bond breaking, that is nothing but the propagation stage. Okay, and here is the everything lies here in the difference in energy of activation. See, in case of chlorination only the difference is 1 kilocalorie per mole, and in case of bromination it's 3 kilocalorie per mole. So here we can correlate this difference of energy in energy of activation with the selectivity of the reaction. Okay, so the small difference in energy of activation, okay, the small difference in energy of activation, it means large difference in the selectivity that we can see in chlorination step, in chlorination reaction, in chloride alkyl chloride formation. The energy of activation in the K step, CH bond breaking, homolytically CH bond breaking in the K step, in that one only 1 kilocalorie per mole is the difference. So that's why the selectivity for the free radical chlorination reaction is less, and the difference in energy of activation is more in propagation step, K step, CH bond breaking step is 3 kilocalorie per mole. So as energy of difference in energy of activation is higher, 3 kilocalorie per mole, that's why the selectively the secondary bromide, secondary primary radical will react formation of secondary alkyl bromide, the rate of that reaction is higher. Okay, so the selectivity is for chlorination is selectivity low because difference is 1 kilocalorie per mole only, and for bromination selectivity is high because the difference is 3 kilocalorie per mole. Okay, so difference we have to consider in between the primary halide formation and secondary halide formation. That means K step, breaking of CH bond to generate secondary radical, and breaking of CH bond to generate the primary alkyl halide. Okay, so this is nothing but the uh, difference between activation energy leads or play important role to for the selectivity. Next one. So, why is the difference for activation energy greater for bromination than for chlorination? Okay. So, the next question arises that we have seen why the bromination is selective. Bromination reaction is more selective because to generate primary free radical and to generate secondary free radical from bromination, the energy of activation is higher, 3 kilocalorie per mole compared to the chlorination reaction. Okay, now the thing is why the difference for activation energy greater for bromination and the chlorination. So we will see now the energy profile of these two reactions, chlorination and bromination. Okay, so we will see now energy profile diagram for the bromination and chlorination. So K difference is that in chlorination the K proportion step is exothermic. Okay, so K proportion step in chlorination is exothermic, and in bromination the K proportion step is endothermic. Okay, we'll see on the next slide how they are exothermic and how they are endothermic. So this is because the chlorination forms a strong HCl bond. See, so chlorination after generation of uh, free radical, secondary free radical as well as primary free radical, whatever HCl bond is generating, that one is stronger, having 103 kilocalorie per mole. And after formation of secondary radical for in bromination reaction, so formation of HBr bond is much weaker. The energy needed to this thing, it's 87 kilocalorie per mole. So this is the second factor we can calculate or we can consider for the why the selective bromination occurs, not selective chlorination. Okay, so in this way we will go for the next slide for the reaction coordinate. That means energy level diagram, whatever. So reaction coordinate for bromination and